Okay, awesome. So it looks like I'm live. Hello? Okay, awesome. So it looks like I'm live. Excellent. Okay, so finally I'm live. Okay, guys, actually I just started uh, a few minutes ago. I was talking about the summary of this big proof. I mean, relatively big. So far we haven't seen much big proofs yet, but this one, in my opinion, is relatively challenging and is very close to the spirit of analysis. Basically, here we're given a polynomial with complex coefficients and we wish to give an upper bound for the reciprocal of that polynomial when the absolute value of z is large enough. So the idea is in a polynomial, eventually the dominant monomial will take over, right? Nothing lower order will compare to it, right? When it comes to the magnitude. So here, to prove this upper bound, we actually used both the triangle inequality and the reverse triangle inequality. And it takes some scratch work for us to get there as well. So this is all very common in actual analysis. Here we're still in the stage of kind of the pre-calculus, so to say, for complex variables. Okay, and now let's just to warm up, let's do some exercise. So this is the exercise for section 4 and 5. Section 4 is the vectorial representation of complex numbers, and section 5 is about triangle inequality. Okay, so here, let's see the part C. Part C says Z1 is minus 3 and 1. Z1 is minus 3, 1, ordered pair. Z2 is 1, 4. Okay, there you go. Let's draw the diagram, calculate the sum and difference. It's a nice practice. Okay, so Z1 is minus 3, 1. So this is minus 3, 1, like this. Z2 is 1, 4. This is 1, and this is 4. Okay, so plot the vectors and their sum and difference. This is minus 3, 1, and Z2, 1, 4 is this one. Okay, so let's use the parallelogram law to form the sum. Okay, so this is sum Z1 plus Z2. And this is the difference, Z1 minus Z2. Translate the starting point of the vector to the origin. Okay, this looks way off, so yeah. Okay, let's calculate the actual numbers. Z1 plus Z2 is minus 3, 1 plus 1, 4, and that's a minus 2 and 5. Okay, great. And Z1 minus Z2, that's a minus 3, 1 minus 1, 4. So that's a minus 4 and 3. Oh, actually, minus 4, minus 3 in the third quadrant. So yeah, that's the third question, part C. Okay. Actually, just in case if I ignore chat in the future, I don't want to do that. Maybe I can put it here, but I was worried about if I write and the chat immediately disappears. Is there a good way to avoid that? Let's see. Okay, so let me try to write something and see if chat immediately disappears. Oops, that's what happened. Huh. Is there a way that I can fix chat at a position? So yeah, this is chat. I want to like for some other streamers, I see them, they can put chat on the screen and they can do whatever else. How should I do that? This is chat from OBS, by the way, because I'm not very skilled when it comes to with all the setup and stuff. As you can see, in my past streams, my setup are very extremely minimalistic. Let's just put it that way. I want to put the chat in the corner. Okay, maybe let's not worry about that now. I'll Google it later. Okay, so here, let's keep doing the questions. I'll try to keep an eye on chat on my other screen. Sorry about potentially missing chat messages. So here you have D, which is Z1 equals X1 plus IY1. Once again, I apologize if my writing today is a little bit clunky because I just got a new mouse. I use a mouse to do the live streams and not I don't have a tablet, so this is just OneNote on Microsoft that comes with Microsoft Office. Okay, so let's plot the two numbers. Of course here x1 and y1 can be arbitrary, so let's just put it right. Let's just draw a generic vector in the first quadrant. This is x1 plus iy1. Okay, this is x1 and this is y1. Okay, and x2 is x1 minus y1, so it's just a reflection across the x-axis minus y1 right here. So this is z1 and this is z2. Okay, so the sum of z1 and z2 is exactly 2x1. So that's a real number, like this. Okay, this is z1 plus z2. And z1 minus z2 goes like this. So that's a vertical vector. If we translate the origin, translate the tip, the starting point of the vector to the origin, and this is what we get. This is z1 minus z2. z1 minus z2 is x1 plus iy1 minus x1 minus iy1. And as a result, we get 2iy1. So that's the visualization and the algebra. Okay, so here this is exercise number 1. Exercise number 2. We are asked to verify the inequalities in section 4, inequality 3. Okay, so I think we did that already when we were discussing section 4. Here, this is section 4. Did I wrote that? This is actually the section 3. Section 4 is vectorial representation. Yes, this is section 4, vector and moduli. Okay, so inequality number 3 in section 4 is this. We already wrote that down. So this is inequality number 3. We actually, did we verify it? Actually, you know what? Let's just do it on the side. Okay, so we didn't. We just thought, okay, this is obvious, right? So this is the saying that the hypotenuse, namely z modulus, is greater, is no less than both of the real part absolute value and the imaginary part absolute value. So verifying this is very easy. Proof. You just let z equals x plus iy. So z modulus, this is the square root of x squared plus y squared. Of course, this is greater or equal to the square root of x squared, namely x absolute value. That's exactly the real part of z absolute value. And an absolute value of a real number is, of course, no less than itself. Very simple. And similarly, here, the absolute value of z is greater or equal to the imaginary part of z. So that's y. Greater or equal to y absolute value, which is the same as the imaginary part of z absolute value, and is greater or equal to the imaginary part of z. Okay, it's very short. So we will consider this exercise done in the main text. Okay, so here, let's just say exercise 2 is done. We're following the 9th edition of Brown and Churchill. So that's the second exercise done. Third exercise is to use established properties of moduli to show that when you have z3 absolute value not equal to z4 absolute value, modulus, whatever you call it, we have the following. We have the real part of z1 plus z2 over z3 plus z4 modulus, okay, less than or equal to z1 plus z1 modulus, okay, plus z2 modulus over z3 modulus minus z4 modulus, quantity taking absolute value. I want to prove this. Okay, so typically when we prove an inequality, we need to do some exploration and quite often work backwards. So this is our scratch work. In working backward, you write your scratch work first, and then you write your proof pretty much following the reverse order of the scratch work. So first we notice something. So why do we need this assumption, right? Usually we start with the assumption. Why do we need the assumption? Well, that's because here on the right hand side you have z1 absolute value, or z3 absolute value minus z4 absolute value on the denominator. And denominator obviously can be 0. So this is why we need the assumption. But looking at the right hand side, looking at the denominators on both the left and right hand side, this looks like a reverse triangle inequality. So let's write that down. And this is often the case. The reverse triangle inequality is most likely to be used on the denominator, okay, based on our experience. And this is the pattern, okay. We also use that. We estimated the denominator in example 3, 1 over pz. Pz is a polynomial. We estimated this reciprocal of a polynomial by give a lower bound for the denominator. So we wanted a lower bound for pz absolute value, and that we used the triangle inequality. So reverse triangle inequality, as I said, is often used to give a lower bound for the denominator. And here, the reverse triangle inequality, the most likely reverse triangle inequality, we're going to use the reverse triangle inequality, z3 plus z4 absolute value greater or equal to z3 absolute value minus z4 absolute value, and then taking the absolute value. Very likely to use this one. And because of the assumption, this is also greater than 0. Okay, so on top, what we have? On top, So on top, we first notice there's a real part. So let's just consider the real part inequality. The real part of z1 plus z2 is less than or equal to z1 plus z2 modulus. And then you can use the triangle inequality to write this is also less than or equal to z1 modulus plus z2 modulus. So now you have an upper bound for the numerator and a lower bound for the denominator. So the inequality is now shown. Okay, so let's write the proof forward. Okay, so let's write by, actually, you know what? We didn't actually work backward, right? We just noticed how we can get the, yes, this is a classic text. And the exercises are very reasonable. Okay, so it's great for complete beginners in complex variables. And actually, it is also great for someone who say was never taken real analysis, who did, let's say, standard calculus linear algebra, but haven't done much proof and wanted to get into more advanced stuff. And this is actually a great book to learn proofs. This is actually a great book to learn proofs. There's often, for math majors, usually courses on dedicated proof writing, but for, say, applied scientists who want to get into advanced mathematics, but don't have the time to do a dedicated proof writing course, the best way to learn proofs is simply to, learn the mathematics while doing proofs. So it's killing two birds with one stone. But for that, you need a pedagogical text that is good for self-study, and Brown and Churchill is a classic one. It is such an approachable text, and at the same time, it's rigorous and deep. So it's not as brutal as something like L4. Right? So L4 is known for its extreme economy. L4, complex variables by complex analysis by L4. That's not great for self-study. You really need a good teacher to make sense out of it, unless you have a lot of quote-unquote mathematical maturity. Okay, so by the reverse triangle inequality, we have z3 plus z4 absolute value greater or equal to z3 minus z4 absolute value. Okay, and by assumption, the right-hand side above is positive. Okay, and by the triangle inequality, so the real part of z1 plus z2 actually, by the reverse triangle inequality and 3, inequality 3 in section 4. Inequality 3 in section 4 and triangle inequality. This is what we get. We do plan to finish the whole text of Brown and Churchill by the end of the year. But in the meantime, okay, the immediate objective is to get to the residual theorem and its applications, and perhaps also conformal mapping. And for that, I set the timeline to be the end of August, not August, but end of October. Okay, by the end of August, we wish to at least get to counter integral. But actually, initially, I wanted to do residual theorem by the end of August, but Next week I'm going to be actually quite busy, so that's unfortunately not happening. But at least, okay, this week we hope to get into analytic functions and its properties, and some of its basic properties like the Cauchy-Riemann equation. Okay. Anyway, so that's the immediate plan. Okay, so now let's combine 1 and 2 by 1 and 2. Actually, this font of is called 1 star and 2 star. This is 1 star and this is 2 star. By combining them, we get the required result, the real part of z1 plus z2 over z3 plus z4 quantity modulus. This is greater or equal to, actually this is less than or equal to, yeah, less than or equal to z1 modulus plus z2 modulus over, okay, the absolute value of z3 modulus minus z4 modulus. Okay, so that's about it. Okay, so there you have it, right? That's the result. And let's take a look at the other exercise, which is also proving inequality. So the fourth one is to show that the square root of 2 times the absolute value of z is greater or equal to the real part of z absolute value plus the imaginary part of z absolute value. Okay, so how do we do that? First of all, let's actually think about the geometric meaning of this one. So this is scratch work, as always. For most inequality problem, we need scratch work because there's so little premise. Right? You cannot follow the assumption easily and get to the conclusion. Here, implicitly, there's only one assumption, that is z is a complex number. What do you do with that, right? So, so here, let's draw the picture. So this is a real part of z, and this is the imaginary part of z. And that's a vector, z. Okay, it says the sum of the two rectangular legs, basically, is bounded by square root of 2 times the hypotenuse. Doesn't seem too intuitive, right? Doesn't seem too intuitive, but let's just say, okay, let your z be x plus iy. So what do we want? You want the inequality square root of 2 times the square root of x squared plus y squared to be greater or equal to x absolute value and then plus y absolute value. How do you get that? Right here, x and y are reals. Okay, so and this is equivalent to 2 times x squared plus y squared, and it's greater or equal to squaring. Also, I'm trying to square the both sides. Okay, so the square of the right hand side is x absolute value squared, which is just x squared, and then plus the cross term 2x absolute value, y absolute value, and plus y squared. Okay, and now you can see you have x squared minus 2x absolute value, y absolute value, and then plus y squared. So I'm subtracting the right hand side on both sides. Okay, so this is the same as x absolute value. So now we see what's going on. Right? So that's a true inequality. So basically we're done. So that's the scratch work. And to write the proof forward, starting with this and then deduce backward. Right? So this is a very typical proof of inequality. You try to reduce the desired inequality into something that is more well known. Okay, let z to be x plus iy. Okay, then we have x absolute value minus y absolute value squared, quantity squared, to be positive. So then by expanding that, we get x squared minus 2x times y absolute value plus y squared to be greater or equal to 0. So now let's do, you can say x squared plus y squared is greater or equal to 2x times y absolute value. And we add x squared plus y squared on both sides. This way you get 2 times x squared plus y squared greater or equal to x squared plus 2x times y. Oh, hi Dawn. Thank you very much for joining the stream. Thank you. Yeah. So yeah, just in case, guys, if you don't know Dawn, he's also a fellow math streamer. Actually, let's go check out his stuff. I'll put the link of his channel in the chat. So Don and I have very similar background. He's also in applied mathematics. Okay, so he, as far as I know, and he also makes constant content in applied mathematics, and almost, I think, just based on his content. Okay, the focus of his material. I mean, not just the material per se. Okay, the overall philosophy of the channel seem to overlap with my own a lot. So go check out his stuff. So I posted a community post on Sunday, kind of trying to position the channel. Okay, try to position the channel as applied mathematics channel that focus on the derivations, the theoretical foundations, rather than specific computing packages and lots of technology-heavy visualization. Of course, we do appreciate visualization, but pretty much all the visualizations are hand-drawn. The idea is you don't need a lot of technology to do applied mathematics rigorously. Okay, and people seem to have this misconception. I mean, not in academia, but on a widespread, more for laymen and even among STEM majors, that applied mathematicians always uses technology, and they are quote unquote right applying pure mathematics. And actually, the working process of applied mathematician is not so different from a pure mathematician for a lot of people. Okay, it also consists of theorem, definition, proof. But now you have the extra work of relating your results to reality. Okay, so for example, for numerical methods is typically considered as a branch of applied mathematics. Numerical analysis is a branch of analysis, alongside with real and complex analysis. Right, so it's a branch of analysis. So the numerical analysis is also done in this way: definition, theorem, proof. Instead of just proving the big N exists for a given epsilon, you actually need to calculate big N and give the convergence rate. So there's that. And this is Don's channel. So, and this is what he does. So, for example, he did the chain following of a table differential equation, Taylor expansion to estimate the integral, and Lipschitz continuity. So that's some analysis stuff. Right. And here you see these are all like just old school mathematics, like just a man and a board, one note, or whichever technology Don preferred to use. And recently he also did a live on calculus of variation. This is very much related to the optimal control, which we had one live stream on, and we'll definitely have to come back to that. So yeah, go check out his stuff. and yeah, it's amazing. So this is, you see, this is the calculus variation. So calculus variation, optimal control are very much related. Markov chains. I wish to cover these things sometime in the future, but now I'm kind of having a lot of things on my plate. Geometric interpretation, vector subtraction, PDEs. Nice, PDEs. So I think, yeah, if you're interested in applied mathematics at all, okay, definitely go check out Don. And this is, wow, this is really advanced stuff. Studying PDEs with Rayleigh quotient. This is super cool. This is super cool because this allows you to estimate eigenvalues. So PDEs and Rayleigh quotient. So this is the perfect marriage between PDE and linear algebra. Okay, that's so cool, man. Go ahead and check out his stuff. Okay, more calculus of variation and probability. You see, so there's a lot of overlap with what we do already on the channel. And struggling with topology, right? I did too, man. Topology. So this is in what he does is very similar to so first of all, similar to the material we're doing, and also in the way we're doing things. Okay. Anyway, so excellent. Yeah, it's an excellent channel. Criminally undersubscribed, but go ahead and check out his stuff. And he also has a gaming channel too. Yeah, if you're interested in that sort of thing. All right, so let's get back to, that's a nice break. Okay, let's get back to proving stuff. Two heroes meet. Yeah, I think, yeah, just in case you guys didn't know, we're gonna have like a how should I put it? I don't even know how to call it, but basically, a few of us math streamers on YouTube are gonna have a collaboration on the 29th. On the 29th, so it's less than 2 weeks. Okay, so we will be doing collaboration as part of what we call this is actually my first time knowing this, called SOMI. It's called the Summer of Mathematical Exposition. Okay, it's already been, I think it's already going on, right? It's already going on Twitch and YouTube. But for the YouTube folks, that happens on the 29th. So JC, Leo lectures, and K-Theory, Don and I will be we'll have like a sort of a marathon stream. Not everyone is going to stay the whole duration, but I'll try to hop in on both the morning and afternoon sessions. Okay, so announcement to be made in a few days. Okay, when we're getting to a closer date, because if I announce now, then people are going to forget, right? So it's too far away. Learn my lesson the hard way, actually. Yeah, so coming back to this inequality, and we have basically that's the final goal, right? So this is just you can write it as x squared plus y squared quantity times 2 greater or equal to x absolute value plus y absolute value quantity squared. Okay, and now you have taking the two square roots on both sides, you get square root of 2 times the square root of x squared plus y squared greater or equal to x absolute value plus y absolute value. Okay, so this is square root of 2 times z absolute value, z modulus greater or equal to the absolute value of the real part of z plus the imaginary part of z. Okay, so this is what we need, and stopping to take notes in the time frame. Oh, okay, so you guys, yeah, so for sure, like if you want me to go back to any part of my previous note, please let me know, and I will stop for you. Okay. Okay. Yeah. So just say, do you mind if you go to, yeah, if you mind to go back a little bit, you can just say that, because sometimes people forget which exact section, right? So just, do you want me to scroll back? You can just say, do you want me to scroll back? Right? You can you scroll back, and I will do so. Okay. Oh, yeah. I'll try to pay attention to the chat. Okay. So if there's a question or a theorem that you want to go back for, because well, it's the live stream, you don't have control, right? So the thing is, I really wish to have like a 4 pieces blackboard on like one in a university lecture hall. But then again, it has its own issue, right? Because some people might watch it from a mobile device. That can be difficult to see the letters and stuff. The font would be too small. So I try to maximize the space as much as possible. Okay, I'm deliberately not using webcam just so that everything is dedicated to the main star of the show, the mass itself. Okay, my face don't really matter, right? So that's the philosophy here. So if you do want to stop for a moment, or re-explain something, go ahead and do that in chat. Okay? Because this is the idea of the live stream. Okay, so as a mass creator, the more content I make, the more I realize I need to improve my knowledge, and this is partly me teaching, partly me practicing, which in my opinion is the best way to learn. Right? You learn by teaching. Right? So, of course, I know because of this like a marathon style stream, it's unlikely to get as many views as just a more polished video, and that's okay. Because I wanted to make sure those videos have the best quality. For that, I need to practice, right? And I figured, why don't I show the process of practicing live? Right? Sometimes I make mistakes, and actually quite often I make mistakes, and I was corrected by chat. And that's a great experience for me. And so that's the overall idea of these streams if you're new to the channel. Okay, so that's question number 4. Let's go. Question number 5. So we wanted to sketch the point, right, given by the inequalities. So sketch region, basically. Sketch the set of points. So that was my cat. Okay, so let's do the sketch of points. So now you have 3 equalities and inequalities, and we wish to represent those equalities and inequality as a set of points on the complex plane. So part A is this. So you have z minus 1 plus I modulus equals 1. So what does it say? Well, this just says that the distance between, you can write it this way, this is equivalent to z minus quantity 1 minus I quantity, absolute value equals 1. So that's saying the distance between z and the point 1 minus I is constant, which is 1. And that's exactly the circle. That's exactly a circle. So here, let's first plot the center, which is 1 minus I. So, okay, so this is, yeah, so this is 1 minus I. 1 and minus I. 1 minus I, so that's 1 minus 1, right? So that's the center of the circle. And the radius is also 1, so that means the circle is tangent to both the x and y axes. Okay, so that's basically the region, right? That's the circle. Let's also describe it verbally. Right, the equation is a circle. This is the circle. The circle centered at 1 minus 1 and with radius 1. Okay, so that's the first one. Okay, so yeah, that's part A, and part B is z plus I modulus less than or equal to 3. So what's that? Well, that's less than or equal to, so this means the distance between z and the point minus I Yeah, yeah. One itself is the radius, right? Because yeah, that's the Don is actually very helpful. He reminded us of a very common mistake because in analytic geometry you have this form, right, for the circle. Let's say x minus a. It's a very helpful tip because we're so used to the form of circle in analytic geometry. Basically, on both sides you have distance squared, but here this is just the distance, the raw distance without the square. So literally it says the distance between z and 1 minus I is 1, not square distance. Okay. Um, okay, awesome. Shah, awesome. Gonna playing this in the background as I read the paper. That's cool. That's cool. So, like, um, use this live stream whichever way you like. You can play as a background while you do your own thing. And actually, I do that to JC's stream. So JC practice math. Uh, I think that's his main channel. Actually, no, his main channel is called Math Can Be a Hobby. So JC Practice Math is his live stream channel that he recently started. So I play his stream while I was doing chores. I'll be frank. And if I hear something interesting, and I'll come back to the PC and do some commentating. Okay. So yeah. Feel free. Yeah, that's great. Thank you very much for hopping in, Shah. So yeah, so here we have the second set, which is an inequality. So it just says that the distance between z and minus I is less than or equal to 3. So that's inside the circle and on the circle. Okay, so let's draw the picture. Okay, so here the center is minus I. There's a point on the y-axis. This is minus 1. That's 0 minus 1 is the center. All right, so first let's describe the region verbally. Okay, this is the region inside and on the circle. Now, that is centered at 0 minus 1 and with radius 3. Okay, so there you go. So if the radius 3, then the highest point should be 2, right? 0, 2, and the lowest point should be 0 minus 4. So that's the circle. Okay, yeah. So that's the circle, and it's inside the circle as well. Not just on the circle, but inside the circle too. So actually, we'll be doing this doing this sort of practice a bit more in the last section of chapter 1, which is called the region on the complex plane. And over there, we'll introduce some basic terminologies from topology as well. What does it mean? What does an open set on a complex mean? On the complex plane mean, right? A closed set, accumulation point, that sort of stuff. Okay. Nothing as crazy as a full-fledged topology class, but those notions are needed when we discuss basic notions in analysis like continuity, limits, that sort of stuff. Okay, so that's why we do that in the last section of chapter 1, which I'm not sure we will be able to get to today. Coming next, I guess. This is part B, sorry, my bad, this is part B. Okay, part B and then part C. Part C says z minus 4I is greater or equal to 4. So that's outside the circle, on the circle and outside the circle. So the distance is at least 4. So here, let's first identify the center. The center is 4I. Right, this is a region outside and on the circle, centered at 0, 4, and with radius 4. So this is the circle. Okay. Let's draw the diagram. Because the center is 0, 4 and with radius 4, it should be tangent to the x-axis or the real axis. So it's like this. So that's the circle, and we're talking about the region both inside and out. Sorry, not inside, on the circle and outside the circle. Because once again, because equality can attain inequality can attain equality in the description. So this is 4i, and the radius is also 4. That's the highest point should be 8. Okay, so it's include the circle and outside the circle. So let's just highlight that. Just a personal story, okay? I took real analysis and complex analysis in the same semester, along with ODE, like an intermediate ODE class when I was an undergrad. And I'll be completely honest, I loved complex analysis, but I hated the real analysis. But nowadays, my opinion has kind of turned around. I mean, I don't hate complex analysis, but I appreciate real analysis a lot more. But I think the reason is because, okay, the ODE class and the complex variable class are very similar when it comes to style, to just calculus, with some proofs that aren't super abstract. But for real analysis, the entire flavor is so different from all the math I've learned earlier. It's just something that is not, I got used to very quickly. So that's why I hated it. And there's a feeling that whenever I'm writing a proof in real analysis, somebody is ready to pounce on me and say, oh, that's not fully rigorous. And there's, especially in the early part of real analysis, there's so little things you can use. There are two sources of difficulty in real analysis, like just, I mean, not on a non-technical level, okay? At the very start, okay, you start from the definition of real numbers, there's only so few things you can use, okay? Everything needs to be proved, and you don't have a lot of things that you can use, right? Sometimes the statement looks absolutely obvious, but you can't prove it, and it's very frustrating. And in the later part of the real analysis, there's so many damn results and definition that you need to remember. Okay, because I mean, I kind of did it the wrong way because I was trying to memorizing things instead of internalizing. For example, I pretty much memorized the definition of compactness as if it was like God-given, and I didn't know the motivation at all. So it was an axiom pushing exercise for me, when it comes to real analysis, and I hated it. But then again, if I hadn't taken that, I would not survive grad school, because in grad school I had to take measure theory, functional analysis, and a rigorous PDE. So the thing is, it paid off. Real analysis really paid off, and quite. I think it would be fair to say that if I hadn't taken real analysis, I wouldn't be able to survive those things at all. So yeah, it definitely paid off. But complex analysis, the bottom line is complex analysis is a much more gentle experience. Just my experience, okay? Your mileage may vary. Okay? It's not as scary as real analysis, in my opinion. Anyway, and for Brown and Churchill, actually, it's not because complex analysis is easy, okay? Not like that. So complex analysis uses certain results from the real variables. For example, in real analysis, you need to prove, or at least give a theory, right, that the real number is complete. The completeness of R is assumed here, is assumed in complex variables. Like in real analysis, you have to prove things like the extreme value theorem, which is very abstract and non-constructive. Right? although the theorem itself is quite intuitive, right? The statement itself is quite intuitive, extreme value theorem. But in real analysis, you have to actually prove it, which is very abstract. And in complex variables, a lot of times we're just assuming results such as the extreme value theorem. Anyway, enough of that. Now let's come back to the exercises. Now we're doing exercise number 6. So here it says we want to show that z1, z minus 1 quantity, okay, z1 minus 1 quantity equals z plus I quantity is a line. This represents a line. This represents a line through the origin. Actually, is z line. Is line through origin with slope 1. So we can do this both algebraically and geometrically. Let's first do it the algebraic way. Okay, so first let's do the algebra. So here we can square both sides. We can get z minus 1 modulus squared equals z plus I modulus squared. And we're just going to write z equals x plus iy. So this now reads x minus 1 plus iy modulus squared which equals x plus I, that's sorry, x plus iy plus I, that's x plus I times y plus 1 modulus squared. And then, so expanding this the squared modulus, this way you get x minus 1 quantity squared and plus y squared, which equals x squared plus y plus 1 quantity squared. Okay, and now we can expand the square, so this is x squared minus 2x plus 1 plus y squared, which equals x squared plus y squared plus 2y plus 1. Okay, and you have x squared cancel, y squared cancel. Yeah, so the only term that survives are x and y. Hold on a second, is that right? Oh, sorry, the slope should be minus 1. What am I doing? The slope should be minus 1. So all that left is minus 2x and 2y on each side. So this way y is equals minus x. And we're done. Okay, and the geometric way says, geometrically the equation says the distance between x and the point 1 equals the distance between, sorry, not x, okay? The distance, let me rephrase. Geometrically, the equation says the distance between z and 1 and the distance between z and minus I are the same. Okay, so this is the geometry. So it says distance between z and the point 1 equals the distance between z and minus I. So there's a theorem from classical Euclidean geometry that says that's a line. Now, if z satisfies this condition, then z has to be on the line of the perpendicular bisector of a line segment that connects the point 1 and minus I. So this is a line segment, okay, that contains that connects 1 and minus I. And the perpendicular bisector lies, bisector is where Z lies. Okay, so Z is on the perpendicular bisector if and only if, in fact, its distance between the 2 points are the same. Okay, and here, well, now it's kind of geometrically obvious, right? Because the origin 0 is on that line. The origin is on that line, and of course, because of bisection, it also passes through the midpoint. What's the midpoint? The midpoint is half and minus half. And of course, this will have the slope of -1. So that's the geometry. Okay, cool question. Next up, question 7. So that so it's similar to our polynomial reciprocal estimation here in the example in the main text. So now we wanted to show something else. Okay, so we want to show that we wish to show for r sufficiently large, for r, which is a real number, okay, r positive sufficiently large, we have the following lower bound estimate for a polynomial. Okay, p of z, which equals a naught plus a1 times z plus all the way to the highest order term, which is an, z to the n, satisfies the following inequality. Satisfies p of z modulus is greater than 2 times an absolute value times z quantity, z modulus to the n, whenever you have z modulus greater than r. Okay? Okay, so let's first try to explore things a little bit. Okay, basically, this is what we want to show. Okay, so we wish to give a lower bound in terms of basically a multiple of z modulus to the n, right? So I guess we still want to somehow group together the contributions from the lower order term. Actually, this is less than. Sorry, my bad. This should be less than. What am I doing? This should be less than. This is the upper bound. Okay, upper bound for the modulus of p of z. So this is our goal. Let's do some scratch work as usual. Because writing proof is not a linear process. It doesn't go like this. It doesn't work like calculating an integral. You just follow a mechanical recipe, and just like you don't typically write proof that way. Instead, you explore a bit and write a draft, kind of like writing an article, and then change the wording somehow. Usually, it takes some exploration and reorganization to complete a proof. Okay, so once again, let's try to group the contributions from the lower order term. So let's write p of z as w and then plus an z to the n. All right, so this means p of z modulus, this is less than or equal to w modulus and then plus, okay, sorry, I have to specify what w is, where w is the sum of the lower order terms. So w is a naught plus a1 of z plus all the way to an minus 1 times z to the n minus 1. Okay, so by the triangle inequality, you got this estimate. So an times z to the n absolute value, and of course the dominant term is just an absolute value times z absolute value to the n. So we want to show what we need is this. We need this w to be less than the same thing, right? An quantity, an absolute value times z absolute value to the n as well. So this is what we want. This is what we need. So, okay, our need is, okay, let's just say, okay, our need, let's work backwards. This is what we need. So let's think about what our need implies. Well, this means this. So you got, you can divide by z modulus to the n on both sides. You can say an over z quantity to the n. And this is plus a1 over z modulus to the m minus 1 goes all the way to am minus 1. Sorry, there should be a, okay, my bad, there should be a modulus here. Should be a modulus here. So this is, because this actually, what I just wrote here don't make sense because you can't compare non-real complex numbers. So w is defined this way, okay? W is defined this way. We need w modulus to be less than that. Okay, you can compare modulus, that's no problem because it's just comparing two real numbers, but you can't compare complex numbers. Okay, the meaning for that precise statement was explained, okay, on the 14th, on the stream on 14. So the exact statement is that complex number is not an ordered field, but it can be an ordered set. Ordered field is different. Basically, you cannot introduce an order relation on the set of complex numbers so that it is compatible with arithmetic. And the exact explanation was given on the 14th stream, where we introduced all the necessary definitions and the proof. The proof is actually super short. It's laying out the definitions that's a bit wordy. Okay, you have to say exactly what an order means, right? What is an ordered field, and what are some of the most basic properties of ordered fields, and how exactly the complex number violates that. Okay, and it can be put into a ordered set. Now, let's say if you just ignore the arithmetic and you want to order on its own, you can actually define an order. But that's an ordered set, not an ordered field. An ordered field is an order. It is an ordered set and a field, but with extra condition. That is to say, the order relation has to be compatible in a way with the arithmetic operation, and the exact definitions and axioms are listed here. Okay, so I'm not going to say anything more than that. I just wanted to reiterate that complex number is not an ordered field. That's what we actually mean when we say, oh, you can't compare complex numbers. Okay, yeah, that's a review of the 14th stream. Anyway, so coming back here, we need the modulus of w to be less than the modulus of an times z modulus to the n. Okay, so that's what we want. And our need here, our something we can imply our need actually. Because w has an obvious upper bound. So w can use a triangle inequality to less than to estimate w. W absolute value is less than absolute value plus all the way to an minus 1 absolute value z modulus, okay, to the n minus 1. So we just want this to be less than the desired goal. And for that, let's divide by z modulus to the n on both sides. Okay, modulus here, modulus here, modulus here, modulus here, over z modulus, and is less than an absolute value. And this is doable because every single term here tend to 0. Every single term tend to 0 as z modulus tend to infinity. Okay, so therefore we can just pick. How many terms are here? From here we have n terms. Here we have m terms. So we can pick, okay, pick r positive so that we're going to pick r positive so that, so each term on the left hand side, each term on the left hand side, they actually have a nice pattern going on, right? That's say ak over ak modulus over z to the m minus k modulus z modulus to the m minus k. That's what I mean. Okay, so we want this to be less than an modulus over n. Now whenever z modulus is greater than r. And this is possible because each of these terms has a function of z modulus tend to 0 as z modulus tends to infinity. So this is always possible, and we want this to be true for all k, for every single term on the left hand side. So for all k equals 0, 1, all the way to m minus 1. Okay, and that's it. That's it. So that's our scratch work, and you can now write the proof forward. Okay, right. So so this sort of proof is very similar to the epsilon big N, epsilon delta kind of proof. Okay. Just a quick question. Anyone interested in being a mod in chat? I mean, I still don't have a mod. I've been streaming for some time. I mean, I do have Leo as mod, I guess. I'm pretty sure I do have Leo as mod, but if you guys want to be a mod, let me know. Okay. Yeah. Okay. So let's do a proof, the formal proof, the actual proof, and it's written forward. Okay. So here, let's first define R. Let's first define R and verify the property. Okay, so there you go. Pick R positive such that for all k equals 0, 1, all the way to m minus 1, ak absolute value over z modulus to the m minus k is less than an modulus over n whenever z modulus is greater than r. Okay, z modulus is greater than r. So that's possible. Okay, so there you go. We have that, and now let's suppose z modulus is greater than r. So we want to pick r, okay, up front, and then verify the property. Okay, so there you go. Then you have pz p of z modulus less than or equal to a naught. Actually, let's write it this way. Okay, let's first group the terms. Should we do that first? Yeah, let's do that. So P of Z, this is, let's write P of Z as follows. So you have um, say a naught over z to the n, z to the n plus a1 to the z to the n minus 1 plus all the way to an minus 1 over z, and then plus a n quantity times z modulus to the n. Okay, so yeah, we can do that. Okay. There's no inequality yet. Okay, so now let's use triangle equality for the first one. This is less than or equal to triangle equality a naught absolute value over z modulus to the n plus a1 absolute value over z modulus to the n minus 1 plus all the way to am minus 1 modulus over z modulus, and then plus an absolute value. So that's the triangle inequality applied to the first, well, the bigger term, okay, the bigger factor. So that's pretty much it. Okay, because each of these terms are less than, this is less than, okay, each of these terms, this is less than an absolute value over n, and you have n terms of them. Each of them is less than sorry, not an minus 1, but an absolute value over n. And together you get 2 times an absolute value. And that's exactly what we need. So we're done. Okay. So that's the proof for the exercise 7. Okay. Next up we have exercise 8, which is also done because exercise 8 is to show a property about modulus. So this is exercise 8. The modulus of z1 times z2, which we've been using quite a bit. The modulus of the product is the product of modulus. Also, this is exercise 8. So that's already done. And Vernon this morning mentioned that it has something to do with number theory as well. So basically, in the process, I mean, the verification isn't difficult, but in the process, we obtain an interesting identity. Namely, you can break the sum of 2 squares of integers. Okay, so you can break the sum of 2 squares into a sum of 4 squares, and whenever these coordinates x1, x2, y1, y2 are integers, this way you can write a sum of squares of 2 integers into a sum of square of 4 integers, which can be useful in number theory. Vernon said this morning that the identity lemma of that theorem is called the sum of 2 squares theorem, reducing the case of composite numbers to prime numbers. How awesome is that? Okay, but here this is a complex incarnation. So this is actually nothing short of a miracle. This identity right here is nothing short of a miracle. It looks rather innocent, and it's very similar to the identity in absolute value for real numbers. But here it is actually a little miracle that makes it true. It has to do with the fact that you can break the sum of 2 squares into a sum of 4 squares. Otherwise, this identity can't be true. All right, so coming back, that means exercise 8 is done. And now we have one more exercise to solve. So now we wish to show that use induction to show z to the n modulus is z modulus to the n equals 1, 2, and so on. Okay, yeah, when n equals 1, that's a trivial case. And we also actually, just wanted to mention, like, if in case you guys didn't know, we also had a little dispute over how to write induction proofs on the 14th. And I'm going to repeat the lesson here, okay? If you've already seen this, I apologize, but I do want to make this extra clear to the new viewers. So on the 14th, we assume that the triangle inequality is already proved, because actually at this point, okay, not even triangle inequality is proved, because we wanted to prove it after we introduced conjugate. So we've been assuming the triangle inequality, so we've been delaying its proof. Okay, that was the situation. So here we wanted to show there's a corollary of the triangle inequality that says basically for finite sum of complex numbers, a sum of complex numbers with finitely many terms also satisfy the triangle inequality. Of course, we've been using that a lot. So the crux of the controversy last time was that whether the base case should be n equals 1 or n equals 2. So for base case n equals 1, of course, you get a tautology. Z1 absolute value less than or equal to Z1 absolute value. That's trivially true. And then I went on with the inductive step, okay, assuming the inequality is true for some n, and we want to prove this is true for n plus 1. So Chad was telling me that because I only have n equals 1 as my base case, you can't go from P1 to P2. The P1 and P2 are a shorthand, okay? It stands for the proposition for n equals 1 and the proposition for n equals 2. So in this inductive step, what I'm supposed to do is show that for any little n, okay, for any little n in big N, you can go from P of n to P of n plus 1. But Chad was telling me you can't go from P of 1 to P of 2 because P of 1 is tautology. But then I countered that by saying, well, P of 2, that's the classical triangle inequality, which has to be proved separately, of course, which has to be proved separately. And right now we're just using it. So we can say P of 2 is a true statement. So therefore, P1 implies P2 is true. Okay, we're not missing P1 implies P2 because P1 is true. This is tautology. P2 is also true. It's just that they have to be proved separately. So we do have induction proof. However, regardless, the core message is that P2 has to be proved separately. If you treat n equals 2 as the base case, well, you have to prove P of 2 separately as well. So essentially, there's no difference. As long as you proved P of 2 separately, treating n equals 1 as a base case or treating n equals 2 as a base case makes no difference. But perhaps for readability, it's perhaps a better idea to write n equals 2 as a base case. So I did concede on that. Okay, and so here this seems like a rather pedantic distinction, but really the core message, like the crux of the dispute, is that P1 implies P2 is true or not. Here we do have that being true. Whenever you don't have that, however, the whole proof of induction can fall apart, right? That's the famous example here. This is the so-called horse problem. For every set of n horses, all the horses in the set have the same color. Obviously, this is false. But you can quote-unquote prove, which is obviously this is false, okay? So this is a cautionary tale. You can't prove this by induction. And here, this is why. Because you can pause it. Actually, the discussion was this morning on this false proof. Basically, you can't go from P of 1 to P of 2. P of 1 says, for every set of 1 horses, all the horses in the set have the same color, which is trivially true, because in that case, you only have 1 horse. right? So the thing is, for P2, you can have a subset you have two subsets of elements. You have two subsets that are singleton. Of course, the base case applies to each one of them, but you can't combine them into a bigger set and say x1 has the same color x2. Right? So this way, P of 1 cannot go to P of 2, and therefore the whole induction proof falls apart. Okay, so the bottom line is, as long as you have P1 implies P2, then it doesn't matter if you treat n equals 1 or n equals 2 as the base case. And in both approaches, P of 2, in the case of the triangle inequality corollary, you have to prove P of 2 regardless, separately. So here, coming back to this induction, we have faced a similar situation. We choose n equals 1 or n equals 2 as the base case. N equals 1 is trivial. N equals 1 is a tautology, once again. N equals 2, for n equals 2, you rely on this non-trivial property of the modulus. It relies on that. So let's just use n equals 2 as a base case as a result, okay? And we'll do things in similar manner if we encounter such induction proof. We treat n equals 2 as a base case whenever n equals 1 is a trivial case, a tautology. So this is a proof. So we prove the result using an induction on n. Okay, so here's the base case. N equals 2. Actually, let me note it here. And note that statement is trivial when n equals 1. Because that's just z modulus equals z modulus. Okay, so base case n equals 2, and here you have z squared modulus, which equals z times z modulus. So by the exercise 8, this is z modulus times z modulus, which is z modulus squared. Okay, so that's the base case, and the inductive step is as follows. Okay, let's assume the statement true. For some n. For some n equals m, where m is a natural number. Okay, so this is our induction hypothesis, IH. Okay, then we wanted to show the same statement is true for m plus 1. So let's start by writing z to the m plus 1. Okay, so let's write it as z to the m modulus, z to the m times z together modulus. So now you can use the base case to break it into two factors, which is z to the m modulus times z. Okay, so this is the base case. And now you can use induction hypothesis because you assume the statement is true for n equals m, so the first term now becomes z modulus to the m times z modulus. So that's the base case. Okay. Oh, sorry. That's the induction hypothesis, IH. Okay, that's induction hypothesis IH, and you get Z modulus to the m plus 1. And that's exactly what we need, as needed. So we have successfully go from n equals m to n equals m plus 1. Therefore, this means, as needed, the statement holds for when n equals m plus 1, assuming induction hypothesis. Assuming the induction hypothesis. So that's the objective in the inductive step. And finally, to finish up the proof, we write by the principle of mathematical induction. By the principle of mathematical induction, we have z modulus to the n equals z to the n modulus. And this is true for all n in big N. That's the end of the proof. Okay, so that's exercise number 9. Okay, finally we're done with the exercises. We can now start a new section. Actually, this is it. I think it's probably a good idea to start a new note. Okay, start a new note, which is August the 17th, Brown and Churchill, complex variables. Okay, so the next section is on complex conjugate, section 6. We're still in chapter 1. Okay, complex conjugate. This, once again, shouldn't be a new topic, but let's just go over it rather quickly. So here, the complex conjugate what's nice about Brown and Churchill, actually Brown and Churchill's series, there are several textbooks authored by Brown and Churchill. Actually, 2 of them and another one by Churchill alone. Okay, what's nice about these textbooks, they all present knowledge or material in a bite-sized fashion. For example, this section is just about complex conjugate. So you can easily say, time yourself, say, okay, I'm going to read through the main text in an hour and hopefully do some exercise. Because right now I'm doing the same process, but I'm doing it like out loud. So it takes extra time. But for yourself, you can kind of do it silent. Right? But still, the same idea is repeatable, right? You take notes and you do the exercises with pen and pencil. You can't just read it as a novel. It doesn't work like that. Right? And so what's nice about Brown and Churchill is that each section is not overwhelming. Okay, so L4 probably introduced everything in just one section, 1 to 5 in one section. And actually, I do have my L4. Right, so in case you guys don't know what I'm talking about, there's a famous textbook, okay, called Complex Analysis by L4. Complex Analysis L4. Okay, so this is a very famous textbook. Unfortunately, it has now gone out of print, and the price is absolutely insane if you want to get a physical copy. Yeah, so people say, why is L4's complex analysis impossible to find? It's kind of somehow out of print, but this is an extremely famous textbook. L4 himself is a Fields medalist. I think he is one of the first Fields medalists, Lars L4. Finnish mathematician, worked in Harvard. Yeah. L4 made a monumental contribution to complex variables, and also in particular Riemann surfaces. Okay, so he worked in Harvard. I think he got the first ever Fields Medal. See, 1936, L4. Okay, so he wrote at least in the Western world, the canonical text on complex analysis. It's very short. It's in the style of Baby Rudin. But the problem is it's difficult if for self-study. So this is a classic complex variable. It's a classic text on the subject, and almost certainly referenced in any more recent texts which make heavy use of complex analysis. He also wrote other significant books, including Riemann surfaces. And this came out in a similar year, I think in the same year actually, with Baby Rudin. That's the principle of mathematical analysis. So this can be very much be considered as the complex analysis counterpart to Baby Rudin. Okay, Brown and Churchill is not like that. Brown and Churchill is very approachable. Okay, for example, one of the reasons it's so approachable is because it divides topics into bite-sized pieces. Okay. Okay. All right. This is a complex conjugate. Complex conjugate of x plus iy. Complex conjugate of x plus iy. Z equals x plus iy is z bar equals x minus iy. Okay, and the geometry is rather obvious. So it's just a reflection of a complex number across the x-axis. So that's the x, okay, and y. And z bar is the reflection of z across the x-axis. Okay, so this is z bar. You have this nice symmetry going on. So this way, it's immediate that, okay, my cat pressed on the keyboard, that's why. Okay, so therefore, it is immediate that you have z bar, z double bar equals z. Okay, that's double reflection to get back to z. And also, it's also obvious that z bar modulus should be the same as z modulus. Okay. This is equation 1 in the main text, section 6. All right. So let's continue. What are some of the other properties? Okay. So you have a bunch of other properties that are very easy to show. Here you go. The other properties we have are the following properties. So the thing is, complex conjugate also interacts very nicely with the arithmetic operations. So for example, you can break the line in the sum like this. And the proof is very simple. Let's just write it on the side. So this is called equation 2. Okay, this is equation 2, and the proof of 2 is very simple. Right. So let z1 equals x plus iy, iy1. z2 equals x, okay, x2 plus iy2, and as a result, z1 plus z2 bar is x1 plus x2 quantity plus I times y1 plus y2 quantity taking complex conjugate. and you have x1 plus x2 minus I times y1 plus y2. And but this is exactly the same as x1 minus iy1 and plus x2 minus iy2. All right, and this is exactly z1 bar plus z2 bar. So we're done. Okay, very simple proof. So that's equation 2. Equation 3 says you can do this for subtraction as well. That's z1 bar minus z2 bar. And you also have line breaking property, so to say, for the product, which is z1 times z2 bar equals z1 bar, all right, times z2 bar. Okay, and next up you have the bar of z1 over z2 quantity. So the conjugate of the quotient is also the quotient of conjugate. So this is extremely well behaved. Okay, so you have these equations are labeled as 3, 4, 5, 6. Okay, just 3, 4, 5. 3, 4, 5. These three equations. And of course, when you write 5, you assume that z2 is non-zero. Okay, we'll stop writing this every time we wrote a quotient. Right, this is classic convention. Whenever you write a quotient, it is assumed that the denominator is non-zero. Okay, and next up, you also have other properties. Property number 6 that says the following. Property number 6 that says the real part of z is z plus z bar over 2. The imaginary part of z is z minus z bar over 2i. So that's property number 6. Okay, this is property number 6. Also very easy to prove. The next property is 7. So here you have 7, which says z times z bar is z modulo squared. So we often use this in fraction, okay, multiplying by the conjugate. This is 7. The proof of these are all very easy. I believe some of the exercises of this section involve some of the proofs, so we'll save that for the exercise. Simply state these, okay? And let's see an example of using equation number 7. I mean, we already seen that earlier, actually. So this is example 1 of section 6. So you can use that to simplify fraction. So you got minus 1 plus 3i over, say, 2 minus I. Let's multiply by the conjugate of 2 minus I on top and bottom. So we've got minus 1 plus 3i times 2 plus I divided by 2 minus I times 2 plus I. All right, so after the expansion, you got 5 at the bottom, and on top you got minus 2, minus 3, okay, plus 6i minus I. So there you go, you got minus 1, this is minus 5 over 5, so that's minus 1, and plus 5i over 5, that's an I. Okay, that's it. Okay, simple example. Here, you can use this identity. You can use 7. You can use 7 to obtain properties of moduli. Okay, so using 7 to obtain properties of modulus. Okay, so let's see how that's done. For example, you can proof of the multiplicative identity, proof of z1 times z2 modulus equals z1 modulus times z2 modulus. So let's do that. Let's see how that's done. Well, here, let's consider the square modulus, because 7 is about square modulus. So you have z1, z2 square modulus equals z1, z2 times the conjugate of z1, z2. Let's use the conjugate identity for multiplication. This can be broken into z1 conjugate times z2 conjugate. All right, and let's use the commutative law, distributive law, and whatnot, and write this as z1 and z2. Sorry, z1 times z1 modulus, z1 times z2 conjugate, my bad, times z2 conjugate. And now you have the z1 modulus square times z2 modulus square as needed. So that's the proof of this one. Okay, so and yeah. Okay, and this is labeled as equation 8. This is equation 8. Okay, so and next up you can also do that to another identity, which I believe is left in the exercise. z1 over z2 modulus. Okay, and I think today we will finish the exercises for this section and call it a day. So, and as promised earlier, with conjugate we can prove the triangle inequality. Now, using purely complex methods, okay, without any reference to geometry. So this is equation 9, and we wish to prove that as well. Okay, not right now. Okay, we'll be. I think we'll be seeing them when we deal with the exercises. Okay. All right. Okay, so that's pretty much just this section. The main text is very succinct. Okay, it's very, how should I say? It's just a definition of complex conjugate and some properties. Let's now do the exercises for this section. Exercise. So it says now use the properties of conjugate and moduli to show the following. Okay, so show the following. So A is z bar plus 3i taking conjugate is z minus 3i. Actually, we can do it in a one-line proof. Okay, so first break the bigger line, z bar plus 3i. This is z double bar plus 3i bar. And you get z minus 3i. Done. Simple. Part B. Part B says iz bar is minus I times z bar. The proof is also simple. Iz bar equals I bar times z bar, and you get minus I times z bar, and we're done. 7, you got 2 plus I quantity square taking conjugate equals 3 minus 4i. Proof. Okay, so yeah, and you can do it in different ways. I guess to use a property, you might as well just break the conjugate first and then multiply. Okay, let's do that. So 2 plus I quantity squared taking the conjugate is now 2 plus I conjugate times 2 plus I conjugate, and that's just 2 minus I times 2 minus I. Do the multiplication, so that's a 4. It's a 4 minus, actually, you just write it as this way. So it's 2 minus I quantity squared, so that's a 4 minus a 4i, and then plus a minus 1. So that's a 3 minus 4i, and we're done. Yeah, this is part C. Sorry, this is part C. Part D. Part D says the following. Part D says you got 2z bar plus 5 quantity square root of 2 minus I, and then taking the modulus. Okay, and let's see what that's what's that supposed to be. Well, we have a multiplicative property, right? So actually, this is the result. This is the result. Is the square root of 3 times the 2z plus 5 modulus. All right. So let's do the proof. So on the left-hand side, you got 2z bar plus 5 quantity times square root of 2 minus I, taking modulus. So this is the modulus of 2z bar plus 5. Is the modulus of 2z bar plus 5, right? We want to get rid of the bar, but can we do that inside here? Let's try. Okay, let's try that. So here you have first of all, break the moduli this way. Square root of 2 minus I moduli, and that's the square root of 3. This is the square root of 2 squared plus a minus 1 squared, so that's the square root of 3. You get a square root of 3 times the here. Yeah, so we can write 5 as 5 bar. That's the nice thing about real numbers, right? It's equal to its own conjugate. So you can write it as, and also 2 as well. You can write as 2 bar z bar plus 5 bar. Okay, and now what you have inside of the modulus can be written as one big conjugate, which is the conjugate of 2z plus 5, and then take the modulus. But now we can use the fact that a complex conjugate and the original complex number have the same modulus. This way you can get rid of the bar. So that's the square root of 3 times the modulus of 2z plus 5 as needed. So we're done. So that's part D. All right, cool. So how many exercises do we have? Actually, we have quite a few exercises. There are 15 of them, actually. Okay, so we'll do so. We'll finish up these exercises and we'll call it a day. Right now, it's 10:50. Hopefully, we can do everything in an hour. Okay, speed run. Question 2. Sketch the set of points. Sketch the set of points. So right, so that's the that's part A. Part A says the real part of z bar minus I is 2. So that's the first set. Okay. And to do that, why don't we just write it as okay, to do this, let's just let z equals x plus iy. Write it this way. Okay, so what we have is the real part of z bar, which is x minus iy minus I equals 2. Right? So, well, taking the real part is easy. This is just x equals 2. Just x equals 2. Or you can write it in a separate way. The method 2. Without writing z equals x plus iy explicitly, but it's essentially the same thing. So we know that the real part function is linear. So in the sense that you can is a linear function in the sense that you can write it as the real part of z bar minus the real part of I. So the real part of z bar is the same as the real part of z. Right? Because complex conjugate only flips the sign of the imaginary part. Doesn't change the real part. And the real part of I is 0. So this just says the real part of z is 0. Oh, sorry, the real part of z is 2. And that's a very simple equation geometrically as well. So it just says that the real part is 2, so it's a vertical line, x equals 2. That's it. Okay, what's going on? This is the real part of z equals 2. 2 right here. Okay? X and y axes. So that's the region. That's the set of points determined by this condition. All right. So part B. Part B says the following. It says 2z bar plus I. Okay. 2z bar plus I modulus equals 4. Okay. So you can still use let z equals x plus iy and then substitute, simplify, that kind of thing. But I think there should be a better way. Okay? There should be a better way to avoid complicated manipulation. So let's do that. The idea is we want to express this as the distance of z between the distance between z and another point on a complex plane equals a constant. So that's our goal here. Okay, so let's see how we can do that. Okay, so first of all, unfortunately there's a z bar inside. We wish to get rid of the bar. So let's write 4 equals 2z bar plus I modulus. Okay, so here you have a 2, which is just 2 bar, z bar. So we want, in the distance formula, okay, you want a minus, right? The distance between a point z1 and z2 is the modulus z1 minus z2. So let's create a minus sign. And the nice thing is, I is the conjugate, so this plus I is minus I, and minus I is exactly the conjugate of I. So you can just write minus I bar. Right. Plus I is exactly as minus I bar. Because I bar is minus I. There's double minus here. Oh, that's my cat. So now the inside of the modulus operator is just, oh, cat wants to play. Too much math, he said. Okay. But I don't think it's too much math. There's always more math to be done. 2z minus I modulus, taking the absolute value, and that's exactly 2z minus I modulus. So therefore you have the following, which is z minus half I modulus equals 2. Okay, so basically now you have the perfect geometric form, which says the distance between z and the point half I is 2. So this is the circle. is the circle centered at the point z, the half I, which is 0, 1/2, with radius 2. Okay, let's draw the diagram. The center is on the y-axis, and the radius is 2. This is 1/2, okay, and the radius is 2. Like this. Because the radius is 2, the top point has a y-coordinate of 2 plus 1/2, so that's 5/2, and the bottom point has a y-coordinate of 1/2 minus 2, that's a minus 3/2. Okay, and we're done. This is part B. Okay, so exercise number 3, we need to verify equations 3 and 4. Okay, so these are 3 and 4. This is what 3 says. These are 3 and 4. Okay, so let's copy this down and verify that. Once again, this should be very straightforward, just a computation. Okay, so let proof. Okay, let z1 equals x1 plus iy1, z2 equals x2 plus iy2, and z1 minus z2 conjugate is first let's do the subtraction. You get x1 minus x2 plus y1 minus y2 conjugate, and this is x1 minus x2 minus I times y1 minus y2, and this is exactly x1 minus iy1 minus x2 minus iy2 quantity, and this is exactly z1 bar minus z2 bar. Okay. Right. Okay. So this is the first identity. Okay. Z1 times Z2 bar is as follows. So you got Z1 times Z2 bar equals, okay, the conjugate of this, the conjugate of, say, this is x1 plus iy1 times x2 plus iy2. Expand, and you get, we're tempted to use this property, but we can't do that. That's illegal. We need to prove it, right? So here, this is x1, x2 minus y1, y2, and then plus I times x1, y2 plus x2, y1. And then taking the modulus. All right, so this way you get x1, x2 minus y1, y2 plus, actually minus I x1, y2 plus x2, y1. But this is unclear, so let's evaluate the right-hand side of 4 to see whether it's the same as the left-hand side. Okay, so let's evaluate z1 bar times z2 bar, and that's what? That's x1 minus iy1 times x2 minus iy2, and you expand that, you get x1, x2 minus y1, y2 plus I times minus x1, y2 and minus y1, x2. And so this is exactly the same. Therefore, you have 4 proof. This is exactly the same as the left hand side, so you can write z1 z2 conjugate equals z1 conjugate times z2 conjugate as needed. Okay. So question 3 done. Question 4. Question 4. It says use property for. Use for to show the following. To show A, which is z1 z2 z3 bar equals z1 bar z2 bar z3 bar. So this is very similar to the induction business we did earlier, if you know what I mean. This is part A. Okay, to prove that, it's you just group things into. Right, so four is this property we just showed. Okay, so which says you can break the line in a product of 2 factors. So let's first group z1 and z2 and use the property twice, basically. These are very reasonable exercise for people who just get into proof writing. These 3, okay? So this is z1, z2, z1, z2 conjugate times z3 conjugate. So here we use 4, and here we use it again. z1 bar, z2 bar, and z3 bar. That's the end of the proof of part A. All right, part B is also straightforward. So z4 bar, z to the 4th, okay, taking conjugate is z bar to the 4th, okay? Now proof. So first of all, let's write z to the 4th conjugate as z to the 3rd times z, together taking conjugate. And now you can use property 4 and get z cubed conjugate times z conjugate. And now I'm going to use part A. I use part A just above, because here you have z cubed bar, right? And earlier we have the conjugate of the product of 3 factors, exactly what we needed here. So this is just z bar to the 3rd times z bar, which is just z bar to the 4th. Okay, so that's done. Actually, yeah, I have a Discord message I want to reply real quick, because somebody says any book on ODEs with real analysis backing. So Ming said in a community post that is assumed, but I haven't taken it to be fair. Okay, so okay, I will just answer that real quick. I only assume, okay, I only assume calculus based ODE course. Introductory level. Like various solution methods for ODE. Separation of variables. Separation of variables. Linear ODEs with constant coefficient. Laplace transform, etc. For that, use Edward Penny. Use Edward and Penny. Okay, so that person said he doesn't have the background, and that's totally okay. In fact, I'm going to do a bridge course. So it's very similar style. The Edward and Penny is a classic text on. Hang on, let me say. Okay, Pali, if you can hop onto the stream, I'm talking about it live. Pali, if you can hop into the stream, and we will, and I am right now, I am talking about it live. But in short, Edward and Penny is very standard. It's very standard, similar style to Stewart's calculus. So if you guys have taken a standard calculus course that's mostly focused on calculations, graphing, that kind of thing, but not rigorous proofs, the Edward and Penny is a very good book. Hi, Pali. So so I was talking about the Edward and Penny. So that's the introductory ODE course I'm talking about. Actually, you know what? I was just thinking about, this one. I misspelled Penny in Discord. It's called Differential Equation and Boundary Value Problems. This is a classic text. And do you have any pictures? Yeah. Do we have, for example, the list of content? Like the things I'm assuming that you should know before, say, tuning into the stochastic calculus, stochastic differential equation series, which we just had one episode on, as well as PDEs. So, for example, my series on SDEs and PDEs assumes ordinary differential equation at the level of Edward and Penny. Okay. Do we have the list of content? Edward and Penny. Yeah, this is AI, but I want to see the actual thing here. Yeah, there you go. First order differential equations. So you need to know how to do separation of variables, basically. And also the other one, important one, is linear first order differential equation. Use it a lot. For example, in what we call stochastic calculus, stochastic differential equation, Ornstein-Uhlenbeck process. So this is the stochastic version. This is the stochastic version of linear first order differential equation. So this is absolutely critical for following along the SDE series. We already did the Ornstein-Uhlenbeck process in both the physics, I think the stochastic process for physicists, and stochastic differential equation episode 1. Okay, so that's absolutely needed. And here we have some modeling stuff. Numerical approximation, Euler's method, and Longo-Kutta. This is also assumed. This is also assumed, but will be reviewed. Will be reviewed as we go along the stochastic differential equation series. And you know what? You know what? Here, I'm just saying this. I'll make a bridge course on ODE. I'll make a bridge course on ODE, just like how we where we have it. So here, basically on we have a series on like a bridge series on how to write proofs, intro to proof analysis series. If you guys didn't know about that, so that's like a bridge course for measure. Basically, that's what I had in mind. Okay, introduction to proof and analysis. Right now, we did a few episodes. Okay, this is the idea of a bridge course. Because of the the prerequisites that I said in the community post. I'm assuming certain things. Okay, but I'm not assuming real analysis. This is a bridge course called Intro to Proof Analysis. I want to do something similar, but for ODEs, like a rapid, like the most basic skills to get into things like PDEs and the stochastic differential equation without a full course on ODE. Okay. But anyway, coming back to book for self-study, this is a great book. It's like the standard. Okay, it's very similar to Stewart's calculus. Linear system and matrices will cover that. Linear system, perhaps not matrices. Okay, but linear system for sure. Here actually it has a self-contained introduction on vector spaces. So it's not assuming linear algebra. It's great if your linear algebra background is a little bit weak. But basically, you can appreciate the linear algebra formulation of differential equation. Higher order linear differential equations. This is also needed. Higher order differential equation, eigenvalue, eigenvectors. Yes, you need that. Linear system, wow, you need that too. Metric multiplication, yes, you need that too. Nonlinear system, yes. Laplace transform, yes. Power series, perhaps not. Okay, so pretty much I think I'm assuming the entire book. Yeah, I think I'm assuming the entirety of Edward Penny with very little exception. Okay, because it actually overlaps a lot with linear algebra too. Now, linear algebra, like the introductory linear algebra, which include vector spaces and eigenvalue stuff. Okay, so yeah, sounds like a great idea. Okay, I'll do like a bridge course, maybe 5 or 6 episodes, not as comprehensive as the whole textbook, but just enough stuff so you can get into ODE and PDE. There you go. Okay, so and for like a proof-based ODE course, ODE book, okay, there are various levels. So one great example is by ODE by I think Burkhoff and Rota. ODE, Burkhoff and Rota. Yeah. So this is a classic on ODE, Burkhoff and Rota. This contains full proofs. Okay. How many citations does this one have? Only 6? Are you kidding me? Oh, that's the book review. Okay, the book review has 6 citations. But basically, this is a standard. This is standard. Okay? And if you're really insane and you aim for full generality, there is this book called Theory of Ordinary Differential Equations by Coddington and Levinson. Came out in the 50s. The 50s is a great time, I don't know why, for Baby Rudin style text. Tons of books were written in like Baby Rudin style. This is a Baby Rudin for ODE. It is extremely rigorous. And many of the results in this book are hard to find in modern textbook. Okay, so this is proof-based, but you really need to know your real analysis extremely well. Okay, including some measure theory to read this. Okay, but as far as like my content is concerned, Edward and Penny will give you, well, I mean, it's not just sufficient, it actually is kind of mandatory. Okay, anyway, I'll make a bridge course along the way with the OD and the SD and PD stuff. Okay. Anyway, I hope that's a good answer. Okay, I mean, ideally, seriously, because ideally, I really think ODEs, the topic of ODE should be taught alongside with calculus. Because you can easily incorporate chapter 1 into Calc 1 as an application of integrals. Instead of calculating a bunch of areas, and stuff, why don't we just solve differential equations as the main objective? because that's historically what happened. And you can talk about modeling as well. Okay, so yeah, just as a fair warning, do not ignore the numerical stuff because Euler's method is needed for SDE, called the Euler-Maruyama method. The Euler-Maruyama method is the stochastic counterpart of Euler's method. It's a numerical method, okay? And it's used, for example, in the diffusion model, which is coming this Saturday, okay? Once again, I don't claim to understand this already. This is going to be this Saturday on the 22nd. It's going to be me trying to figure out how diffusion model works, okay? On a mathematical meaning, okay? I don't mean open up a package and see how the AI generate a bunch of stuff. That's not what we're talking about, okay? This is a math channel. It's not a tech channel. So, yeah, we're trying to understand the mathematical foundation of diffusion model, and which includes SDEs and Euler-Maruyama method, okay? So, for example, let's just search that, Euler, yeah. So this is the SDE that underlies a lot of the network stuff, score network. So you need the Euler-Maruyama method to solve it, which you cannot understand without knowing the Euler's method for ODE, this one. So do not skip this stuff. Okay, so pretty much everything in this book is considered mandatory for following along the SDE series. Okay, anyway, I think I started to repeat myself, so I'll stop talking about this. Okay. Okay. Comment. Oh, love this channel. That's great. Okay. Anyway, so let's finish the remaining exercise. Okay. Stream is getting a little bit long. 5. Verify property 9 of moduli in section 6. What's that? Oh, right. We want to verify this one. We want to verify, yeah, this one right here. Okay, proof. How do we do that? Well, I think all we need, you just need to show 1 over z2 modulus is 1 over the modulus of z2. That should be enough. Okay? Actually, you know what? Let's follow the original proof for the multiplicative property. We use the square modulus and then take advantage of the complex conjugate. I think that's the idea. I think that's what the author had in mind when they asked us to verify that. So let's try that. Okay, so let's first write the squared modulus. Okay, the squared modulus is z1 over z2 times z1 over z2 quantity taking modulus, and then they use the property here. Which one? Yeah, this one right here, 5. I mean, we haven't verified 5, right? We haven't verified 5. I think we'll be asked to do so in the next exercise. This is 5. So using 5, you're able to distribute the conjugate into both top and bottom of the fraction. So the z1 bar over z2 bar. And this is, of course, z1 times z1 bar over z2 over z2 times z2 bar. Okay, and that's exactly z1 modulus square over z2 modulus square, and that's exactly what we need, so we're done. Okay, so I think we will be asked to verify 5, this equals this, in one of the exercises later. So let's do that. Okay. Are we even asked to do that? We didn't, no? That's weird. Why we aren't asked to verify that? Actually, you know what? Let's do a proof of 5 here. Because usually this book is very, as I said, this book is very rigorous. But at some point, I guess the author just figured, it's an easy exercise, you should do it yourself. But he or she should at least, they should at least mention it, right? So anyway. Okay, so what do we want here? What do we want? We want to show, need to show z1 over z2 quantity bar, quantity taken conjugate, is z1 bar over z2 bar. So how do we do that? Well, first of all, let's do some scratch work. Of course, direct computation works, but we just wanted to make use of as many previous results as possible. So that's another lesson, okay, meta lesson for proof writing. Okay, math is cumulative. When you prove something, you can use it. After you prove something, you can use it. This is how math is developed. You don't always start from square one. Right? So, yeah. So you can use what we just proved, right? So here we have our objective, right? That's the conjugate of a fraction. So let's first write the fraction as z1 times 1 over z2. Hi, Steve. Thanks very much for hopping in. Right? So you can use the multiplicative properties. That's just z1 bar times the conjugate of 1 over z2. Can we say something about that? Right? We want that to be z1 bar times 1 over z2 bar. So this is what we want. Hey, thanks for hopping in. So can we show this? Can we show this? Well, I mean, we can probably just. I'm too. You know what? I'm just gonna give the x coordinates and y coordinates to show this. Shouldn't be too complicated. So for that we need 1 over z2 quantity conjugate is 1 over z2 conjugate. This is what we need. Okay, so let z2 to be x2 plus I y2. So you have 1 over x x2 actually, you know what? This is unneeded because we have also the trick for multiplying by 8. We can deal with conjugate. Sorry, we can deal with fraction using the conjugate trick. Okay, I'm not even going to use this scratch work. So I want to use new material. That's the idea. I want to use new material so that we can practice new material. So z1 over z2. Of course, you know what I'm trying to say. If you just let z1 equals to x plus iy and z2 equals to x2 minus iy, just do the brute force calculation, compare both sides. It works, but it's not very, so to say, refreshing. Okay, we want to use new results as much as possible. So to handle the fraction, we're going to use the property of the conjugate, namely if we multiply the conjugate on top and bottom, conjugate of the denominator top and bottom. This way the denominator becomes a real number. This should make things easier, because now at the bottom you have z2 modulus squared, and top you have z1 times z2 bar, together taking conjugate. And now because of the bottom is real, so that you can factor that out, you just get 1 over z2 modulus squared times z1 z2 bar. Okay, that's nice. So quantity taking conjugate. So now use the property of the conjugate with multiplication. So z2 modulus square at the bottom, and here now you have z1 bar times z2 bar and bar. Okay, so this is just z2 on its own. And now we can also rewrite z2 modulus square as z2 times z2 bar. And on top you have z1 bar z2, because z2 double bar is z2, and now z2 cancels. This way you get z1 bar over z2 bar. And we're done. Okay, so that's the proof of 5. Okay, even though in the text it did not explicitly ask us to do so, but I think it's worth verifying. Okay, all right. So now you have the next exercise, which is 6. We wanted to verify the following. Verify A, which says the conjugate of z1 over z2 times z3 quantity is z1 bar over z2 bar times z3 bar. And I believe the proof is just one line. So first, let's use 5. Okay, the property 5 we just proved. z1 over z2 z3. Oh, without the bar, quantity conjugate. Using 5, you have the following, which is z1 bar over z2 times z3 bar. Okay, and now let's use 4 to break the line, to break the conjugate line at the bottom. So you have z1 bar over z2 bar times z3 bar, and we're done. Easy. Part B. Part B, you have z1 over z2 z3, taking the modulus to be z1 modulus over z2 modulus times z3 modulus. The process should be very similar. Okay, so here we're going to first use 9. We're going to first use 9 to break the modulus to both the denominator and the numerator. So there you have it. Z1 over z2 z3 modulus by 9 equals z1 modulus over z2 modulus times z3 modulus. Oh, actually, no, not so fast. It should be z2 times z3 modulus, and then use the 4. Use 4. Use 4, and you get z1 modulus over z2 modulus, z3 modulus. Okay, that's also done. Nice. That's number 6. Let's keep going. Example 7. We want to show the following, which says the real part of 2 plus z bar plus z to the third modulus is less than or equal to 4 when z modulus is less than or equal to 1. So you see, I was trying to cultivate the habit or the preference, so to say, of not immediately writing z equals to x plus iy every time you want to prove an identity or an inequality, because sometimes doing so isn't fun. Okay, isn't very illuminating and can be very complicated. And instead, try to work with z and z bar directly. Okay, that's the preference here. Okay, so you can use some scratch work, I suppose. You can use some scratch work, but let's just try to do it mentally. Okay, so first of all, you have a real part. You need an upper bound, right? So we've seen that earlier. This can be bounded above by the modulus of what's inside the real part. Now you can do it that way, and then you can also apply the triangle inequality to what's inside. And that's exactly what we need, because 2 plus the modulus of z bar, which is less than or equal to 1, and then plus the modulus of z cubed, which is also less than or equal to 1, which is exactly 4. So this is very straightforward. So one of the situations in proving inequality that you can actually just like kind of follow your nose to go from the left hand side to the right hand side. Typically you need some kind of scratch work, but here is actually very straightforward. This is just less than or equal to the modulus of 2 plus z bar plus z cubed. Okay, and then use a triangle inequality. You get 2 modulus plus z bar modulus, and then plus z modulus cubed. Okay, actually let's not so fast. Let's just, this is triangle inequality. Okay, and this is the same as 2 plus z modulus plus z modulus cubed, which is less than or equal to 2 plus, don't give up. Give up on what? Yeah, of course. Yeah, don't give up in general. I suppose that's what you mean. I'm not giving up at all. Okay. Yeah. So this is 7. So we're done. Okay. So that's the end of 7. Next up, 8. 8 shows that. Okay. So I'll just copy the screenshot here. So this is what question 8 says. So it shows that in section 3, that if z1 times z2 equals 0, then at least one of the numbers z1 and z2 must be 0. Give an alternative proof based on the corresponding result for real numbers and using the identity 8 in section 6. So what is identity 8 in section 6? Well, that's identity 8. Identity 8 is this one. This is identity 8. Okay. So I think we want to do something about modulus. We wanted to use modulus to prove the same identity, to prove the same fact. Okay, so at least one of the numbers z1 and z2 must be 0. This is an OR statement. That is z1 equals 0 or z2 equals 0. For OR statement, we can negate one of the statement and prove the other. That we mentioned in one of our earlier live streams, also on complex variables. I think I did that here. Yeah, proof technique. Let P and Q be propositions. To prove P or Q, we can do one of the following. Assume not P and then prove Q. So you negate one and prove the other. And here's the justification. Okay, P or Q is logically equivalent to not P implies Q. You can check their truth table. They're logically equivalent. Okay, and here we use that technique to prove if z1, z2 is 0, then z1 is 0 or z2 is 0. And there we assume z1 is non-zero. Okay, this way z1 has a multiplicative inverse. Z1 multiplicative inverse exists. So you can write Z2 as Z2 times 1, and 1 can be rewritten as Z1 times Z1 inverse. And use associativity, you can combine Z1 and Z2, but then by the assumption that is 0. So 0 times Z1 inverse is exactly 0. So we have accomplished our goal. So now we have modulus at our disposal. So let's do it using the modulus way. So proof. Here, Z1 modulus and Z2 modulus are both real numbers. So you can use the property of the real numbers. If two real numbers multiply and equals 0, one of the real numbers must be 0. Okay, so here, let's first start by writing assume the if part, right? Assume Z1, Z2 is non-zero. And what do? You say the Z1 and Z2, assume Z1 and Z2 is non-zero. Let's also assume and Z1 is non-zero. We need to show Z2 is 0. Okay. Okay, so by the assumption you have Z1, Z2 product, modulus is 0. That's 0. And since Z1 is non-zero, Z1 modulus is positive. Okay, and as a result, you have Z1 modulus times Z2 modulus is 0, and Z1 modulus is positive. So therefore, Z2 modulus must be 0, and as a result, Z2 must be 0, as needed. So we're done. Okay. All right. Next up. So question 9. It says show if Z modulus is 2, then we have an upper bound for this expression, that is the modulus of the fraction, that is 1 over z to the 4th minus 2z squared plus 3. Okay, and this is less than or equal to 1 over 3. Proof. Okay, so this sort of inequality, okay, this sort of upper bound estimate is super useful in contour integrals. When we talk about, that's chapter 4, okay, chapter 4, contour integrals. Integration of complex numbers, integration of complex functions along a curve of some sort. So anyway, so here we have a fraction, and based on our experience, in particular this example right here, this example in section number 5, I believe, yeah, in section number 5, triangle inequality, we need a lower bound for the denominator, and that typically amounts to using the reverse triangle inequality. So here we're very likely to use a reverse triangle inequality for the bottom. Okay, and before we do that, actually here, oh no, what's up with my cat? She's got, oh no, she's got allergies again. Poor kitty cat, man. Oh no. Can you guys hear the cat purring on the side? She's sitting next to me. Poor baby. Actually here, it should be 4, okay? My bad. This should be 4. Minus a 4z squared not 2z squared. Okay, so we need a lower bound at the bottom. Now that's the idea. So first of all, actually, we notice you can factorize this. You get z to the fourth minus 4z squared plus 3. This is z squared minus 3 quantity times z squared minus 1. Okay, so we need a lower bound for this product. So why not try finding a lower bound for each of the factors, right? So z squared minus 3 quantity by the reverse triangle inequality is greater or equal to the absolute value of z squared modulus minus 3 modulus. Okay, this is reverse triangle inequality. And what's that? Well, because here, this is just z modulus squared minus 3. But z modulus is 2, so that's a 4 minus 3, taking absolute value, which is 1. Okay, and let's do the same for the other factor. First, apply the reverse triangle equality, which gives you z squared modulus minus 1 modulus, taking the absolute value. Okay, and this is z modulus squared minus 1, which is 4 minus 1, which is 3. So then you're pretty much done, because 1 times 3 is 1. Exactly what we wanted on the denominator. So here, therefore, you have 1 over z to the fourth minus 4 z squared plus 3 modulus, this is equal to 1 over the modulus of z to the fourth minus 4z squared plus 3. Okay, and this is, well, here you see this is less than or equal to, actually, you know what, let's keep factorizing. Okay, this is the same as z squared minus 3 modulus times z squared minus 1 modulus. And this is less than or equal to 1 over 1 times 3, which is 1/3, as needed. And we're done. Okay, nice. Actually, you know what, guys? To speed things up a little bit, I'm just going to do screenshots over the questions. This way I don't need to copy the question. Okay. So yeah, this is question 10. I want to prove that z is real if and only if z bar equals z. Okay, prove. Okay, so yeah, let z equals x plus iy. Okay, then z is in R is equivalent to x plus iy is in R, which is equivalent to y equals 0. Okay, when y is equal to 0, then this is equivalent to what we want is z bar equals z. So this is x plus iy equals x minus iy, which is the same as z equals z bar. And we're done. Okay, so this is part 8 done. B. Okay, so next up, so z is either pure or real or purely imaginary if and only if z bar square equals z squared. Okay, so, well, actually, you know what, let's start with z bar squared equals z squared. This is equivalent to z squared minus z bar squared equals 0. And then you use the factorization and write it z plus z bar times z minus z bar. So you can write this as 2 times the real part of z, and then times 2i times the imaginary part of z equals 0. So therefore, this is the same as the real part of z equals 0, or the imaginary part of z equals 0, which means z is real part is 0. That means z is purely imaginary. Or z is real. Okay, so we're done. Okay, that's number 10. Number 11, let's do the here. Number 11 is induction problem. And it's very similar to all the other inductions we've done so far. So basically, we've seen this pattern again and again, right? So you have a statement that's true for n equals 2. And you want to generalize this to finitely many terms. And use induction for that. So here actually we use n equals 2 as the base case. So there's no controversy over whether n equals 1 should be the base case or n equals 2. So we just start with n equals 2. Okay, so here that's the proof. A. You have the base case that we prove the results using an induction, or should we prove each result? That's better. Using induction on n, right? So that's it. So you have the base case n equals 2, z1 plus z2 quantity bar equals z1 bar plus z2 bar. That's just exactly what we've seen earlier. That's property number 4, which is true. Okay, and now let's do the inductive step. Assume the property true for some m. Okay, assume A holds for n equals m, where m is for some m in the set of natural numbers. And you need to prove this is true for m plus 1. So then, okay, no worries. Bye, Steve. Thanks for stopping by. Then we have the following, which is z1 plus z2 all the way to zm plus 1. Okay, and this can be broken into, say, z1 plus all the way to zm quantity. Thanks very much, Steve, for your gift. Appreciate your generosity. Yeah, I suppose these are very basic exercises for you. Steve is very advanced. Steve knows a lot about things like mathematical physics and functional analysis. So looking forward to learn from Steve. So next up, we use a base case, z1 plus all the way to zm, taking conjugate, and then plus zm plus 1 conjugate. No, that's the base case. That's the base case. And now you can do the decomposition for the first term using the induction hypothesis. Okay, Z1 bar plus all the way to Zm bar plus Zm plus 1 bar. Induction hypothesis as needed. Actually, let's write the induction hypothesis here over this equality. Okay, so finally, to wrap this up, say by the principle of mathematical induction, just say by PMI, you have for all n equals 2, 3, and so on, Z1 plus all the way to Zn conjugate is Z1 bar plus all the way to Zn bar. Okay, so now you have that. You have part, now this is part B. Part B we have, yes, it's pretty much the same proof, huh? Pretty much the same proof, actually. Okay, so just write that real quick without much explanation. Base case, once again, n equals 2 is Z1 times Z2. Quantity conjugate is Z1 conjugate times Z2 conjugate. So that's what? That's exactly which property over here? That's property 4. That's property 4. So we have that. Oh, actually, I think I mislabeled the earlier part. This was not true, but rather, this is not 4, but rather equation 2. This should be, oh no, what did I do? Okay, this is true because of equation 4. Earlier should be true by equation 2. That was a mislabel. Okay. Okay, and now let's do the inductive step. Assume B holds for n equals m for some m in big N. This is our induction hypothesis. Then what we have is the following. So taking the product of Z1 all the way to Zm times Zm plus 1, and then complex conjugate, you can break this into, using associativity, okay, so Z1 times Zm quantity times Zm plus 1, taking complex conjugate. Okay, and now you can break that into the Z1 times Zm complex conjugate, and then times Zm plus 1 conjugate. Okay, so this is the base case. Good news is I'm getting much better with my new mouse. So this is Z1 modulus all the way to Zm modulus times Zm plus 1 modulus. So that's as needed. Okay, and here we use induction hypothesis. So finally, to finish this up, we say by the principle of mathematical induction, for every n equals 2, 3, and so on, you have Z1 times all the way to Zn conjugate equals Z1 conjugate times all the way to Zn conjugate, and we're done. So that's exercise 11. All right, next up. Next up, I'm making a screenshot, okay, so damn it. Okay, perfect. So yeah, this is the equation 12. So this is a classic result in algebra. So basically, this tells us that the root of polynomials with real coefficients okay, must appear in complex conjugate. What does that mean? So what this result implies is that, okay, if z is a root of a polynomial with real coefficients, then z bar must also be a root. Okay, let's see. So showing this is completely trivial because so showing this, you can just use our previous result. And the left hand side equals a naught bar plus a1z bar plus a2z square bar all the way to an z to the n bar. Right? This is the previous exercise. This is 11 part A. Okay, and now use the 11 part B to write it as a0 bar plus a1 bar z bar. Oh, the cat is very chatty, by the way. a2 bar times z bar squared goes all the way to, yeah, cat be like 12. Time to get to sleep. I know, right? I'll finish up there's only 3 more exercises left, actually. Z bar to the n. This is 11b. This is 11b. And now we can use the fact that a's are all real. This is ai are real. And you have a naught plus a1 z bar plus a2 z bar squared plus all the way to an z bar to the n. And that's it. That's done. But what this implies is actually very significant. So let's say you have a polynomial that is a naught plus a1z plus a2z squared all the way to an z to the n. Right? So if that polynomial has a root, say z, then by this identity, z bar must be a root, because if you substitute z bar into the same polynomial, that's just the polynomial evaluated at z taking conjugate, right? But if z is a root, that means you have a conjugate of 0, therefore it's still 0. Okay? So there's some symmetry going on with the polynomial with real coefficient. If z is a root, z might be complex, then z bar must also be a root. Okay, and this actually has a great application. It actually has a great application in 3D rotation. Basically, this theorem, okay, the fact that complex conjugate must appear the roots of a real coefficient polynomial must appear in complex conjugate appears in part of the proof that why every 3D rotation has an instantaneous angular velocity. Very cool idea, okay? So actually, I mean, we can't do that right now because it's kind of late. I need to get to sleep really quickly because I need to wake up at least 6:30 tomorrow morning. Okay, so sorry for mentioning that amazing fact only in passing. Next up, exercise 13. Okay, this is exercise 13. Exercise 13 shows that the equation z minus z naught modulus equals r is the equation of a circle basically can be rewritten this way. Well, it seems like we just need to expand by squaring both sides. Right, so you got z minus z naught modulus equals r. Squaring both sides, you get z minus z naught modulus square equals r squared, which can be written as z minus z naught times z minus z naught. The conjugate equals r squared. Okay, keep expanding that. You have z, and by the way, these are all equivalent. Okay. Z minus z naught times z bar minus z naught bar, which equals r squared. And that's exactly z times z bar minus z times z naught bar minus z naught z bar plus z naught bar equals r squared. Okay, so notice something here. So those two terms are complex conjugate of each other. So this is equivalent to, first of all, this is z modulus squared. Yeah, and this is what? This is, this can be seen as minus the quantity of z times z bar plus z times z naught bar taking conjugate. Okay, and then plus z naught modulus squared equals r squared. In the middle, you have the sum of a complex number and its conjugate, which is exactly twice of the real part. It's 2 times the real part of z naught bar. And then plus z naught modulus squared, this is r squared. So that's exactly what we wanted, so we're done. Okay, that's 13. Next up, okay, so this, god dang it, why can't I screen frickin' shot, man? Okay, finally. Stop being so pesky. The mouse? What's going on with... I just want to move the damn thing. Can I do that? Okay, I can't, apparently I cannot move things. Okay, that's fine, doesn't matter. I'm not happy with this mouse, actually. I don't know, I want to return this. Okay, anyway, coming back to the exercise. This is the second last exercise of the day. We want to show that here, the expression 6 for real part and imaginary part, this means the real part is half of z plus z bar, right here. This is equation 6. We want to use this to show the hyperbola can be written in complex form. Okay. Okay, so basically here, x squared, let's say 1 equals x squared minus y squared. Okay, x is the real part of z, and y is the real part of the imaginary part of z. So you use the formula for the real part and imaginary part. So that's z plus z bar over 2 quantity squared minus z bar over 2I quantity squared. Okay, let's keep expanding. You get 1/4 of z squared plus 2z z bar plus z bar quantity squared minus z squared plus 2z z bar minus z bar squared. Okay, and this is exactly what? Oops, I forgot. This should be plus. Should be plus because of the 2i. 2i at the bottom is squared to minus, cancel out the minus sign. That's basically what happened, and it should be a minus sign here. So the cross term cancels. That's what happened. So this is half of z squared plus z bar squared. Okay, this is a plus z bar squared, and this is exactly what we needed. Therefore, we're done. Z squared plus z bar squared equals 2. That's 14. Okay. Next up, 15. So now we finally proved, okay, the debt is now paid. Thank goodness for that. The triangle inequality is now proven through this exercise. Okay, so triangle inequality is proven. So here, starting from step 1, expanding the product, expanding the square of the left-hand side. So look at the square modulus, z1 plus z2, squared modulus. This is z1 plus z2, right, times z1 plus z2 conjugate. Of course, this is just z1 plus z2 times z1 bar plus z2 bar. Okay, so this is by expansion, you get z1 times z1 bar plus z1 z2 bar plus z2 z1 bar, and then plus z2 z2 bar. Okay, and here in the middle you can, I think we already used this trick earlier, because in the middle you notice that here this is just z1 times z2 bar taking conjugate. You can put these two together, group these two together, and finally plus z2 times z2 bar as needed. Okay, so part A is done. Part B, why this is in the middle, you have this inequality. Okay, so in the middle here you have z1 z2 bar plus z1 z2 bar. This is twice the real part of z1 z2 bar, and that's exactly equation number 6. Okay, so this is less than or equal to 2 times z1 z2 bar. We have that inequality from earlier, and this is just 2 z1 bar times z2 bar, z1 modulus times z2 bar modulus, and z2 bar modulus is the same as z2 modulus, so therefore you get 2 z1 modulus, z2 modulus. Okay, so now we can combine the results. Okay, so from part A and B, you have z1 plus z2 modulus square. This is less than or equal to z1 bar, that's z1 modulus squared, plus the middle term, which has upper bound of 2 z1 modulus z2 modulus, and then plus z2 modulus squared. And that's exactly just z1 modulus plus z2 modulus. Okay. Quantity squared. And therefore, by taking square roots on both sides, you have z1 plus z2 modulus. This is less than or equal to z1 modulus plus z2 modulus. Okay, and we're done. All right, that's it for today. Okay, that's it for the live stream. Okay, so yeah, next up, next time, I don't know when. Okay, that's unfortunate because recently, especially next week, I'll be very busy. So But next up, our goal is to discuss the exponential form of complex numbers. We'll be doing roots, that kind of thing. Roots, nth root of the complex number. And also regions on the complex plane. Open sets, closed sets, bounded set. Anyway, that's it. Thanks very much for hopping into the stream. Bye.